Welcome to the first module of Engineering Problem Solving with Ease. Let's get started. So the topics we'll cover today are entering and solving equations, units and unit conversions, parametric tables, lookup tables, plotting, and arrays. And at the outcome of this module, students will understand how to use basic features of Ease for solving engineering problems. In order to complete the module, students must complete first the online topic lectures, complete the end of module quiz, and hand in the end of module homework. Solving systems of equations is often necessary for mathematical modeling of engineering systems. This means representation of a physical system using a system of equations that are the result of theory and simplification. If we look at most engineering systems, they're far too complex to describe with a single equation, and typically result in a number of coupled equations and differential equations. Ease provides an environment to solve this coupled complex systems of equations. An important distinction that separates Ease from formal programming languages such as C or Fortran or even MATLAB is that Ease solves equations rather than solving assignments. So the difference between an equation and an assignment is shown with this simple system of two equations, which are actually identical. The top shows a setup of equations where the values on the right hand side can be unknown. So we see that the first equation, which is x minus 2y equals negative 5, could not be solved independently from the second equation, which is 2x plus y equals 10. We could rearrange these using algebra, as I've done on the lower set of equations, to result in an assignment. So in an assignment statement, the value on the right hand side must be known. So we could rearrange these and find that x equals 3. So we would assign the value of 3 to x and then plug that into the second equation, y equals 10 minus 2x, in order to find both the values of x and y. So Ease, rather than requiring algebra, allows us to focus on the mathematical model and solves the equations simultaneously. So let's begin learning how to get around in Ease by solving a simple set of equations. We'll begin by opening Ease from the Start menu. When we open Ease for the first time, we'll see an information screen showing us some of the details of Ease. We'll click Continue. Now, as we move into Ease, the first window that we see will be the Equations window. This is where the equations to be solved will be entered. So let's enter our simple set of equations. X minus 2 times y equals negative 5, and 2 times x plus y equals 10. We can now check the equations using either the Calculate check format or by clicking on the check mark at the top of the screen. When we do this, the information tells us that there's two equations and two variables, and no syntax errors are detected. To solve our set of equations, we'll click Calculate Solve. You can see that we could also just use F2 to solve the equations. When we solve the equations, we see a dialog box telling us that the calculations are completed and giving us some information on the solution. When we click Continue, we'll see that the Solutions window appears, telling us that x is equal to 3 and y is equal to 4. There's also more information at the bottom telling us the calculation time and also discussing any possible unit problems. We'll get into that more in future examples. As we saw in our simple example, we enter the equations in the equations window and view the solutions in the solutions window. When working with array variables, array solutions are shown in the arrays window. The residuals of the solution, or the error in the solution, are shown in the residuals window. Other windows include parametric and lookup tables for tabular data, diagram window, up to 10 plot windows, and a debug window. As we go through the semester, you will become familiar with each of these windows. Engineering problems almost always involve some quantities with units. One of the main powers of ease is that it's capable of handling units and ensuring that problems are solved in consistent units. A primary issue that many people have when solving engineering problems is doing the conversion from one form of units to another. Ease will help out a lot in this area. So let's look at a simple example to begin to introduce the following topics on units. First, setting units, checking unit consistency, converting between units, converting temperature, as we'll see this is slightly different than typical unit conversions, using a consistent unit system for the solutions, and then viewing secondary units. So let's consider the ideal gas equation. Pressure times volume equals mass times the ideal gas constant times temperature, and find the mass of air in a 1 cubic foot chamber at a pressure of 20 megapascals and a temperature of 1000 degrees Fahrenheit. We will open ease and first set the unit system. This is extremely important if we're using ease's built-in thermodynamic functions or trig functions, and it's important to do this before we solve the problem to avoid any unit errors. So to set the unit system, we'll go to Options, Unit System, to bring up the Preferences dialog, and go to the Unit System tab of the Preferences dialog box. We can see that there are several options for units, either SI or English, and various combinations of temperature, energy, specific properties, pressure, and trig function unit definitions. It's important to have a consistent method for dealing with units. The method that I use is that I always work in SI units and set my temperature to Kelvin, my energy to joules, and my pressure to pascals. So this is the MKS, or meters kilograms second unit system of units. It ensures that all calculations are in a consistent set of units and avoids any unit errors. If we want to solve a problem with inputs in different units, I first convert to the MKS system, perform the calculations in MKS units, and then to view the results in different units, I convert the answer to whatever preferred set of units I'm going to use for the problem. So now let's enter our equations and our known variables after setting to SI, Kelvin, joules, and pascals. We'll click OK. So we'll first enter the volume that we were given as 1 cubic foot, so 1 foot cubed. And then, as I said, I like to work in MKS units, so I'll use the convert function to convert this from feet cubed to meters cubed. We'll then enter the pressure, which was given as 20 megapascals. And you can see that I'm assigning the units to the numeric values by using square brackets. So I say 20 megapascals, and again, I want to work in pressure units of pascals, so I'll convert from megapascals to pascals. The next is temperature. So temperature is not a linear conversion like we have when we're converting either volume or pressure. So for temperature, we need to use the convert temp function. So what I'm going to do is I'm first going to input the temperature in degrees Fahrenheit and distinguish this variable by adding the subscript F. So I'll input 1000 F to give the temperature as 1000 F to the variable T underscore F. And now I'll use the convert function on T underscore F to convert that from Fahrenheit to Kelvin. So you use T equals convert temp, and we want to convert from Fahrenheit to Kelvin, so we'll say F comma K, and then we're going to convert the variable T F. So again, what this does is it takes the variable TF, which has units of Fahrenheit, and converts from the units of Fahrenheit to units of Kelvin. We'll now enter other known variables. The molecular weight of air, we could look this up, or we'll see later how we can use Ease's built-in functions to return the molecular weight of air. We'll just enter it for now as 28.97 kilograms per kilomole. We'll enter the ideal gas constant R bar as 8,314 joules per kilomole times Kelvin. And then we'll calculate the ideal gas constant for air as R bar divided by the molecular weight of air. And then finally, we'll enter the ideal gas equation, which is PV equals mRT. If we check our equations, we see that there are 8 equations and 8 variables, and no syntax errors are detected. So we can now solve the equations by hitting F2. And this brings up our solutions window. So what we see first is in red, we have 3 potential unit problems detected. And this is due to the fact that we haven't set the units for the calculated variables of mass, R, and temperature. So now let's go to the variable information window in order to set the units. We can get to the variable information window by clicking on this icon, or we can also right click and select variable info. So this brings up the variable information window showing each variable that we have in our equations window, the guess value, which we'll use as the initial value for the iterative solution, the lower and upper bounds, or the search space that it's going to try to find the solution in, some information on the display properties, and then the units that we're using for that variable. So to set the units, we'll click on the box. First, for mass, we'll set that to units of kilograms. For R, we'll set that to units of joules per kilogram times Kelvin. And for temperature, we'll set that to units of Kelvin. So setting these units really brings up the importance of using a consistent unit system. So I know that I'm always going to perform my calculations in for mass, I'm always going to use kilogram. For temperature, I'm always going to use Kelvin, and the resulting units for R would then be joules per kilogram times Kelvin. We can then click OK, solve again, and we find now that we have no unit problems detected. So a few notes on this solution. I mentioned before that Ease has built-in functions to return the molecular weight of air. So we could have replaced this statement MW air equals 28.97 with one of Ease's built-in functions. We could write MW air equals molar mass of air, and delete this statement. So if you're not able to remember the built-in functions, we can go to the function info and see the available functions that are built into ease. So ease has many math and string functions. You can see these ranging between basic mathematic functions, Bessel functions. If you're working in complex math, there's complex math functions. Down here we see our trigonometric functions. Then there's also the unit systems and conversion functions. We have thermophysical functions for real fluids, ideal gases, air-water mixtures, taking values from the NASA tables, mixtures of brines, and then incompressible substances. There's also heat transfer and fluid flow functions, calculating boiling and condensation, heat exchangers, fouling factors for heat exchangers, radiation, considering view factors, and hemispherical emissivity, as well as some transient solutions. There's mechanical design built-in functions, a whole host ranging from moments of inertias and stress concentrations. There's also ease library routines, which you can go through, and then any external routine. In order to use one of the functions, like we just did for air, let's go to ideal gases, and we'll scroll down to molar mass, and we see the example here. So we have air as our fluid. It's going to assign the molar mass of air to MW. We could add this and say MW air, and then click paste. That's going to paste whatever was in the box in the function info window into the equations window. So we see we have MW air equals the molar mass of air. Ease also includes frequently used constants such as the ideal gas constant. So instead of remembering that the ideal gas constant is 8,314 joules per kilomole times Kelvin, we could have used the options constants menu in order to bring up the constants that are available in ease. If we go down to the ideal gas constant, we see that the name to be used in ease, or the name that will be used in the equations window, is R hashtag. This is a gas constant. It gives the value that's going to be used and the units, and you can see the range of available constants that we have in ease. Again, we could click paste. That'll paste the constant into the equations window. So we could assign R bar to our hashtag and either comment or delete the value that we had typed in earlier. We can again solve the problem and see that we get the same solution, and we also have no unit problems detected. Finally, I'd like to discuss secondary units. So if we go to our solutions window and right-click on a variable, let's say mass in this case, we can see that the units are listed. In this case, we've worked in mass in units of kilograms, but let's say that we want to look at this in units of pound mass. We could set this secondary units to pound mass and click OK, and now we see that mass is listed both in kilograms and pound mass. Okay, so now let's look at parametric tables. Parametric tables are extremely useful as a method to vary one or more parameters and observe the output. The best way to introduce parametric tables is to revisit our ideal gas equation example, and now instead of finding the mass of air at one temperature, we looked at 1,000 degrees Fahrenheit before. Let's find the mass of air over a range of temperatures from 25 degrees Fahrenheit to 2,000 degrees Fahrenheit. So let's go back to our ease program. that we solved before. You can see our solution is still present. Now we want to vary the temperature. We're going to vary this input temperature that I called TF. So let's go ahead and comment that. We want to create now a parametric table. To do that, we could click on this parametric table icon, or we could also go to new parametric table. When we click on new parametric table, this dialog box appears. It tells us the name of the table. We could give this some representative name. I'll say example parametric table. And we give it the number of runs. So this will be the number of times we're going to evaluate the solutions in the equations window, or another way to look at this would be the number of rows in the parametric table. We can go ahead and leave it at 10 now. We then need to add the variables to the table. To do that, we'll click on the variables that we want to add to the table. We could include as many as we want, but to keep it easy to look at, I'll just include the mass and the variable T underscore F, or temperature in Fahrenheit, and then we'll click add, and we see that we transfer M and T underscore F from the variables in equations to variables in table. These are the variables that are going to create the parametric table. It's often useful to arrange these in a certain order. I like to have my inputs on the left and my outputs on the right. So I moved TF to the top and M to the bottom. Now we can click OK, and this creates our parametric table. So you can see our parametric table with 10 rows or 10 different runs containing the variables TF and M. We now want to enter the values of TF, and we said that we want to vary this from 25 to 2000. To enter values, we'll click on this downward triangle. This will give us a dialog box that allows us to fill in the values. We could also use this to clear the values for future work. So our first value is going to be 25, and our last value is going to be 2000. There's several different ways that we could do this. We could increment this, we could add a multiplier, or we could do this on a logarithmic scale. We'll look at this in more detail in the written lectures. For now, let's just look at varying it linearly from 25 to 2000, and then we'll click OK. You can see that it fills in the values in runs 1 through 10, linearly varying the temperature from 25 degrees F to 2000 degrees F. That's all we need to do to enter the inputs. As it goes through each of these rows, it's going to effectively take the value out of each row, put it into the equations window, and solve the set of equations. To solve it, we can either click Solve Table using the green triangle. We could go to the Calculate menu, click Solve Table, or we could simply press F3. So let's solve the table, and now we see that each of the runs are solved and the mass is calculated for each of these runs. So now we can move on to plotting. Plotting is really just a graphical representation of data, and this is typically necessary to convey the results of either a model or some type of measurement from an experiment. Two-dimensional plotting is the typical method used to show data, so we'll discuss that here. There is more complex plotting that we'll get into in the future work, where we're looking at three-dimensional plotting available in ease. So let's begin by creating a plot using the data from our parametric table example to highlight some of the key features of plotting in ease. There's more details provided in the written lectures. So we'll return to our parametric table example. We have already solved our parametric table, so you see temperature on the left-hand column and mass on the right-hand column. If we want to create a plot, we could go to Plots, New Plot Window, XY Plot. This would create a 2D XY plot. We could also simply create a plot by selecting this new plot window command. We will then select our x-axis data and our y-axis data. Here we're going to want to plot mass as a function of temperature. So temperature in degrees Fahrenheit would be our x-axis, and our y-axis would be mass. Ease automatically populates the minimum and maximum values and the interval values. We're free to change these as we need to, and we can change them now or we can change them later. So our temperature ranged from 25 degrees Fahrenheit to 2000 degrees Fahrenheit, and you can see that the limits are set reasonably well in ease. For the mass, we span from 1.44 as our minimum value, so E selected a value of 1, up to 7.3 as our maximum value, so E selected a value of 8, and a step size of 1. We're able to select either a linear scale or a logarithmic scale for both the x and y axes. We can also choose to turn on or turn off grid lines. We can add fits to our data by selecting a spline fit to add a smooth line. Here we'll keep the connection linear. We can also choose to automatically update from the data in the parametric table. So if we change some model parameter and reran our calculation, the plot would automatically update. We can also choose to add a legend item. As far as the display of the plot, we can choose the line type, either a thin solid line, a thin dashed line, or thick solid and dashed lines with various types of dashes. I'm going to choose a thick solid line. We can choose the type of symbol. Here I'm going to choose a circle for the symbol, and for the color I will select blue. So then we can click OK, and this creates our plot. So ease automatically labels the axes, so you can see the y-axis is labeled as mass and the x-axis is labeled as T_F. We may want to change this to make it more descriptive. So I will double click on the y-axis label, and instead of just M, I will change this to mass and say OK. And I will also double click on the x-axis label, and instead of T_F, I'll call this temp. Say OK, and move this to a location where it's not interfering with any of the scales. Also, we can do some adjustments to the appearance of our plot. So we selected the symbol as a circle. However, by default it's shown as a relatively small circle. We can use this slider to increase or decrease the size of the symbol. We can also select a different color here if we decided that we wanted a different color for a certain curve. Additionally, we can change the appearance of the plot. We can set the border to either a thick or a thin line. So here I've set it from, it was default as a thick line. Here I've set it to a thin line. And if we click apply, you see that the change is made. We could also change the color of the border. So here I've changed it to red. However, I'm going to change it back to black to show a more professional looking appearance. We can change the type of the grid lines. I'm going to change the grid lines to a dashed line. Click apply, and now we see that the grid appears as a dashed line. I discussed adding a smooth line before. We can do that here as well. Here you can see going from some cubic spline smoothing to no smoothing, and we can set the source of the data and automatically update the data, as I discussed before. I typically, when I'm using automatic update data, I usually set it in here. This allows me to manually select the data that I'm going to be using. So again, the x-axis is t underscore f, the y-axis is m. We can select which data we want in the parametric table and the name of the parametric table here. If we want to use all of the rows in the parametric table, we could select that checkbox. And with that, we've completed the introduction to plotting. All of the variables we've worked with so far have been scalars. That means that they can only be assigned one value. It's often useful to perform multiple calculations and work with variables that can hold multiple values. Arrays serve this purpose in ease. If you've ever used MATLAB, you're already very familiar with array variables. So to get familiar with array variables in ease, let's perform an example where we repeat the ideal gas equation example, now using an array variable instead of a parametric table. So let's go to ease. We're going to find the mass at temperatures of 25 degrees, 500 degrees, 1000 degrees, 1500 degrees, and 2000 degrees Fahrenheit. So revisiting where we left off our ease code, we have the volume, the pressure, we've commented out the input temperature, and we're doing the conversion in temperature. We have the molecular weight of air, our ideal gas constant, and then the ideal gas equation. We're going to replace t underscore f, t, and m with arrays, so let's comment out these in the following equation. So we'll comment out temperature here, and we'll comment out the ideal gas law here. So we want to create an array variable for the input temperature, or what we call t underscore f. So to do this, we could use several different methods. First, to show you how arrays work, we'll do this explicitly and type out each temperature value. So first, we'll type t underscore f1 is equal to 25f. We would do t underscore f2 is 500f. T underscore f3 is 1000f. T underscore f4 is 1500f. And T underscore f5 is 2000f. We then need to perform unit conversions on each value of t underscore f. So to do that, we'll again do this explicitly to show you how arrays work. So the first one would be T1 is equal to convert temperature from Fahrenheit to Kelvin of our array variable T underscore F1. We would then do this for T underscore F2, T underscore F3, 4, and 5. We could then use the ideal gas equation on each value to find the array of masses. So for the first mass, M1, we would use T1. Then for M2, we would use T2, and so on for M3, 4, and 5. Now if we look at our variable information, we have 20 equations and 20 variables. No syntax errors are detected, so we can solve this set of equations. Notice that we have several unit problems, so let's go to the variable information window in order to correct our unit problems. So when we bring up the variable information window, what we'll see is that we have all of the variables listed, so this being both the scalar variables like the molecular weight of air and each individual value of our array variables. We're typically going to want to set our array value variables all to the same units. So to do that, we can uncheck the show array variables box at the upper left hand corner, And now this collapses the array variables into a single variable. So now we can set the units of our mass array to kilograms and our temperature array to kelvins. Click OK. Now if we solve this again, we see that no unit problems are detected. We can go to our arrays table. If we go to Window, Arrays, we bring up the arrays table, and we can see the solution at each individual value of temperature. So this method works fine for an array where we have 5 input values, but you can obviously see how it could become tedious if we were to repeat this for larger arrays or arrays where we were performing multiple calculations. So we can see that we're just repeating these calculations over and over to convert from Fahrenheit to Kelvin and to solve the ideal gas equation. So for this we could use a duplicate loop. So let's go ahead and comment out these lines. Now we'll use a duplicate loop where we perform duplicate. We'll call our index variable I equals 1 to 5. Let's go ahead and close the duplicate loop. And now we're just going to perform the temperature conversion on each variable I. So this will be convert temp from Fahrenheit to Kelvin, and we want to do this for T underscore F I. So this statement inside of the duplicate loop is equal to these 5 equations. We want to do the same thing for our ideal gas law. P times V equals MI times R times TI. So now this statement inside of our duplicate loop is equivalent to these 5 equations. So to clean up the code, let's go ahead and get rid of these 5 equations. We'll again check our equations, 20 equations, 20 variables, and no syntax errors. So now we can solve this again, and we get, as expected, the same answer that we saw before. Entering the values for our T underscore F variable is somewhat tedious, and we can simplify this and condense it down. So let's go ahead and comment out this T underscore F set. And we'll replace this with a single line. So T underscore F, 1, followed by 2 periods, and a 5. We'll reference the first 5 values of our array T underscore F, and we'll set this equal to 25, 500, 1000, 1500, and 2000. So this statement is equivalent to these 5 lines. Again, we can check 20 equations, 20 variables, and we can solve. Again, no unit problems detected because we've already set T underscore F to units of Fahrenheit, and we have the same solution that we had before. We could simplify this a little bit further by using the array editor. So if we go to Edit, Array Editor, we want to create an array that's called T underscore F. So we'll enter the array name T underscore F. And this is going to have 5 rows, so we'll change this to 5 rows. And now we can just enter the values in each row. Then if we press OK, this adds the array T underscore F with the same syntax that we had typed in manually previously. So these are both equivalent ways of creating this input array. It's a little bit more robust and less prone to error if we use the array editor. One thing to note is that you see it's created these comments above and below the variable T underscore F. This tells us that it was created in the array editor, and if we want to modify it later in the array editor, we need to leave this syntax in place. So again, we could solve and we have the same solution that we found before. To wrap up the discussion of arrays, let's look at plotting with arrays. So we can plot from the arrays table the same way that we would plot using values from a parametric table. So we can create a new plot, and instead of selecting parametric table, we can now select the arrays table. Our x value will be t underscore f. Our y value will be m. We can give a symbol, the same that we did before. Make this blue, make this a thick line, and say OK. And now you can see that we've created a second plot where we have our array variable m as a function of our array variable t underscore f. And we could do the same thing that we did before, modifying this plot and making it ready for a presentation. So lookup tables allow data to be stored and accessed at a later time. These can be used in a similar fashion to a spreadsheet in Excel. So we'll show how to create and access data from a lookup table in this module. In the future module where we discuss data analysis, we'll go into a more detailed description of lookup tables and use lookup tables more in depth. So again, the best way to learn to use these is to look at example problems. So we're going to repeat the ideal gas example using a lookup table and an array instead of simply specifying an array. We'll look at the same values of temperatures, 25, 500, 1000, 1500, and 2000 degrees F, and find the values for mass. So let's go back to our ease code. So here's where we left our ease code after the arrays example. Let's just begin by cleaning up our code. So I'm going to go ahead and get rid of these equations. We'll get rid of our t underscore f variable. We're going to look this up from a lookup table. So we'll go ahead and clean up our code. So currently what we have, if we look at checking our equations, we have 15 equations and 20 variables. This is because we're missing the values from that would specify the t underscore f variable. So let's create our lookup table. We'll go to Tables, New Lookup Table. We'll give it some descriptive name. I'm going to call this Example Lookup. And it's going to contain one column and 5 rows that will contain our values of t underscore f. So click OK. Now we create our lookup table. Let's first start by entering the values in our lookup table. We could do this in several ways. We could do it the same way that we do a parametric table, where we increment the values either linearly or logarithmically, or using some increment factor or multiplier. We could also apply a pattern. For now, let's just go ahead and enter the values manually, since we only have 5 values. So 25, 500, 1000, 1500, and 2000 degrees F. We then want to give the column 1 some descriptive names, so let's right click and select properties. We'll call this T in, and we'll give it units of degrees Fahrenheit. So now we have our lookup table created. Next, we need to get the values out of the lookup table and into an array. For this, we'll put the lookup command inside of our duplicate loop. Let's go back and look at the syntax of the lookup command. So the lookup command will have lookup followed by the table name in the first argument, the row number in the second argument, and the variable name that we're going to look up in the third argument. For us, if we want to assign values to the array t underscore f for each value of the array index I, we would use lookup, the name of our lookup table, so example lookup, our row number is row I, and the variable name is tin. So let's go back to ease and enter this in our duplicate loop. And now we can check our equations again. Now we have 20 equations, 20 variables, and no syntax errors, so we can solve. We've already set the units for each variable, so you can see that we have no unit problems. Looking at our arrays table, we have the same results that we would have expected before. So before we end this module, it's important that our codes that we create are useful even after we're done working with them. So for that, it's useful to comment our codes. So first, I'd like to start off by adding some descriptive comment of what the code is supposed to do. So this code I also like to give descriptions of each variable. So this will be volume, so now I've commented the code. At the top, I give some descriptive name. If we start our comment with an exclamation point, it turns the comment to red. I typically do that for the description of the code, though obviously it's not necessary. And then I like to add a short comment for each variable. So we specified V as volume, P as pressure, the molecular weight of air, the universal gas constant, ideal gas constant for air, and then a description of what the loop is doing. So this is reading values from a lookup table and then solving the ideal gas equation to find mass. A description of what this command is doing. We're reading values from the lookup table, we're converting temperature from Fahrenheit to Kelvin, and then solving the ideal gas equation to find mass. So this completes the module. The remainder of the module will discuss more details on these same topics through written lectures. You'll then be able to check your knowledge using an end of module quiz, and finally complete the homework that's posted on the Moodle page.